Section 5.3 Nomenclators. From the 15th through the 18th century, the king of substitution ciphers was the nomenclator, used by kings, popes, diplomats and spies alike. Each nomenclator had a list of hundreds, sometimes thousands, of items, single letters, numbers, bigrams, syllables, words and names, providing up to 25 substitutes for each. Nomenclators are more like codes than like ciphers, so they fall outside the scope of this book. Section 5.4 Polyalphabetic substitution. The techniques for solving simple substitutions involve letter frequencies and letter contacts. If you want to design a cipher to defeat this type of attack, a good place to start is by disrupting the letter frequencies and letter contacts. Suppose that instead of using the same alphabet for enciphering every letter, you use two different alphabets. Use the first alphabet to encipher the letters in odd-numbered positions, and use the second alphabet to encipher the letters in even-numbered positions. That is, the first alphabet will encipher the first, third, fifth letters in the message, while the second alphabet is used to encipher the second, fourth, sixth letters. The frequencies of the ciphertext letters now come half from the first alphabet, half from the second alphabet. They are the average of the two sets of frequencies. A ciphertext letter will have high frequency only when it represents high-frequency letters in both alphabets. For example, ciphertext K could represent E in the first alphabet and A in the second alphabet, so its frequency would be halfway between the frequency of E and the frequency of A in normal text. Conversely, a ciphertext letter will have low frequency only when it represents low-frequency letters in both alphabets, say K in the first alphabet and V in the second alphabet. So the ciphertext will have fewer high-frequency letters and fewer low-frequency letters than normal text. If you made a bar graph or histogram of the letter frequencies, the peaks would be lower and the valleys would be shallower. So using two alphabets tends to flatten the frequency counts. The same happens with contact frequencies. Any common bigram, such as TH, will start at an odd position in the message about half the time, and at an even position about half the time. Half the time the T is enciphered with the first alphabet, and the H is enciphered with the second alphabet, and half the time it is vice versa. So the contact frequencies also get flattened. The more alphabets that are used, the flatter the frequencies become. In practice, from roughly the US Civil War until World War I, using about 20 alphabets was typical. There is a statistical test that measures the flatness of the letter frequencies and uses that to estimate the number of alphabets, but it is not very accurate, particularly with more than 10 alphabets. Better methods are described in sections 5.6 and 5.7. Let's look at the historical development of polyalphabetic ciphers. Early forms of polyalphabetic ciphers were developed by Leon Battista Alberti in 1467 and by Johannes Trithemius in 1499, but not published until 1606. Polyalphabetic ciphers begin to take their modern form with the publication of La cifra del Sig Giovan Battista Belasso in 1553. Section 5.5 The Belasso Cipher. The Belasso cipher, invented by Giovan Battista Belasso in 1553, used 26 different alphabets, each of which was simply the standard alphabet shifted a number of places. The 26 cipher alphabets can be displayed as a tableau, where each horizontal row contains one shifted alphabet, like this. The first letter on each row identifies the alphabet, so the top row is the A alphabet, the second row is the B alphabet, and so forth. Balasso was the first to use a key to select which alphabet to use for which letter in the message. By contrast, the Argenti family used a keyword to mix the alphabet. Balasso would write the message horizontally. Above the plain text letters he would write the key, repeated as many times as needed. To encipher a letter, he would find that letter on the top row of the tableau, use the key letter to select the row in the tableau, and then replace the plain text letter by the ciphertext letter directly below it in the selected row. Here is how the plain text letter S would be enciphered by the key letter C. We find the letter S on the top row of the tableau. Its key is C, so it is enciphered using the third row of the tableau. On the third row, directly below S, we find the letter U, so S gets replaced by U. To encipher the word sample with the key CAB using the previous tableau, S is replaced by U. The next letter in the message is A with the key A, so A is enciphered with the top row. It is enciphered as A. The M of sample has the key B. It gets enciphered using the second row and becomes N, and so forth. The resulting ciphertext is UANRLF. Instead of using a tableau, the encipherment can be done using a Saint-Cyr slide, named for the French Saint-Cyr military academy. The slide is shown here in the M position. You can make your own slide from wood, cardboard or plastic. The top double-width row is fixed in place, while the single-width bottom row slides. Rubber bands can hold it taut and in the correct position. Either or both of the alphabets can be mixed. The Balasso cipher is symmetric because enciphering a letter X with a key K is exactly the same as enciphering the letter K with the key X. Ciphers based on adding the key to the plain text or exclusive ORing the key and the plain text tend to be symmetric in this sense. For reasons beyond my ken, the Balasso cipher is now known as the Vigenère cipher, and the cipher invented by Blaise de Vigenère, which is described in section 5.8.2, is now called an autokey cipher. To give credit where due, I will continue to call the cipher invented by Balasso using the standard alphabet the Balasso cipher. With a mixed alphabet, I will call it the Vigenère cipher. I will call the autokey cipher invented by Vigenère the Vigenère autokey. Attributing the Balasso cipher to Vigenère is an example of Stigler's law of eponymy, for Stephen M. Stigler, that no important scientific discovery is named for its discoverer. Some cryptographic examples are the Playfair cipher, invented by Charles Wheatstone, and Morse code, invented by Alfred Vail. Stigler's law itself was proposed by Robert K. Merton, who named it the Matthew effect for St. Matthew.